A separable differential equation occurs when the relationship between variables is structured so that you can use algebra to isolate every x term on one side of the equal sign and every y term on the other. This is the generic form of these equations. The derivative equals a function of x multiplied by a function of y. Solving this follows a strict four-step sequence. First, check the y function for zero roots. Second, separate the variables. Third, integrate both sides. And fourth, isolate y to determine the final function. Recognizing this multiplication structure transforms a complex differential relationship into a predictable sequence of algebraic isolation and standard integration. In this initial value problem, we are given the equation y prime equals 2xy and a specific starting point, y of 0 equals 1. Assuming y does not equal 0, we divide both sides by y and multiply by dx, sorting our variables into two distinct groups. With the variables separated, we apply an integral to both sides. The integral of 1 over y yields the natural log of the absolute value of y, while integrating 2x on the right side gives us x squared plus the integration constant c. To isolate y, we make both sides the exponent of the base e. On the right, e to the power of x squared plus c can be rewritten as e to the c multiplied by e to the x squared. Since e to the power of a constant is itself a constant, we define a new multiplier, tilde c. We plug our initial condition into this equation, substituting 0 for x and 1 for y. Because e to the power of 0 is 1, we find that tilde c equals 1. Our final, specific solution is y equals e to the x squared. The algorithm works efficiently when conditions are simple, but the moment you divide an equation by a variable, you introduce the risk of missing valid solutions where that variable equals 0. When we divided by y to separate our variables, we proceeded as if y could never be 0.
If y actually equals 0, division is mathematically impossible, and the standard separation process fails to capture that behavior. Consider the equation y prime equals negative 2x times the quantity y squared minus y. Before attempting to move the y terms, we must check if the h of y block has any roots where it equals 0. By setting y squared minus y equal to 0 and factoring, we see that y times the quantity y minus 1 equals 0. This identifies two constant solutions, y equals 0 and y equals 1. These constant solutions are valid horizontal lines that satisfy the differential equation. They are legitimate mathematical paths, but they are invisible to the standard integration process if you skip the initial root check. The starting coordinate of a problem dictates whether the mathematics guarantees a single unique path or offers no such promise. We can see this in the equation y prime equals the square root of y. This test uses the same differential equation under two different initial conditions. On the left, we start at a y value of 1. On the right, we start at 0. We will start with the left side. Pause the video here to separate the variables, integrate, and solve for c using the initial condition y of 0 equals 1. Integrating y to the negative 1/2 power results in 2 root y, while the right side becomes x plus c. Using our starting values, we find c equals 2. Squaring both sides produces the function y equals 1/4 times x plus 2 squared. A square root must output a non-negative number, which means the right side of the equation, 1/2 times x plus 2, must be greater than or equal to 0. This restricts the solution to where x is greater than or equal to negative 2. Now we focus on the right side of the screen, where the initial y value is 0. The Picard-Lindelöf Theorem establishes if a solution is unique. In this context, a unique path is only guaranteed if the y-dependent term, h of y, is non-zero at your starting point. Because our equation involves the square root of y, and our starting y value is 0, the term vanishes. This triggers a failure of the uniqueness guarantee. Graphing the results proves that two different functions satisfy the equation simultaneously. We have the constant solution, y equals 0, and the parabolic path, y equals x squared over 4. Both of these valid paths intersect at the origin. Because the theorem's conditions weren't met, the mathematics cannot distinguish between them. Differential equations represent paths of motion. When the starting point hits a critical boundary, where h of y is 0, the mathematical reality can branch into multiple valid trajectories. We will synthesize these mechanics with one final problem, y prime equals e to the negative y, with the initial condition y of 0 equals 1. First, we multiply both sides by e to the y to separate the variables. Integrating both sides results in e to the y equaling x plus c. We isolate y by taking the natural logarithm of both sides, which gives us y equals the natural log of the quantity x plus c. Using y of 0 equals 1, we find that 1 equals the natural log of c, meaning c must equal e. This finalizes our solution as y equals the natural log of x plus e. Finally, we check the domain. Because the input of a logarithm must be strictly positive, x plus e must be greater than 0. This limits the solution to values of x greater than negative e. A solution is only complete once you define the specific domain where the formula is valid. This layout summarizes the 5-step procedural framework. It consolidates the steps of checking for zero roots, performing the integration, solving for the constant, and verifying both uniqueness and the valid domain. Applying this sequence ensures hidden constant solutions and domain restrictions are accounted for in every problem. This systematic approach allows you to navigate the algebraic constraints of any separable differential equation.